Oh no, it appears my eggs have been scrambled. Luckily, I was able to use merge sort to unscramble them. But how does this algorithm work? The main idea of merge sort is that it is a recursive sorting algorithm. This means that it calls itself to sort smaller portions of the array as part of the main algorithm. It's quite simple, only having three main steps. The first step is to divide the array into two equal halves. If the array size is odd, one of the halves can be one element larger than the other, but otherwise they should be as equal as possible. Each half is sorted by recursively calling merge sort on that half. This creates two sorted lists that are half the size of the original list. Finally, a merging procedure is used to combine these two sorted lists into one large sorted list. But what is this procedure, and how does it work? Well, the merging process is also quite simple. It starts by comparing the first element of each of the two arrays that you're trying to merge. Because the arrays are already sorted, this is equivalent to comparing the lowest item of each array. Then, the lowest of those two is added to a new array and removed from the original. We repeat this process using the new first element of each array. This eventually ends up adding all of the elements to the new array in sorted order. And once one of the two arrays is empty, all the remaining elements from the array that still has elements in it can simply be added to the end of the new array. If you found that a bit confusing, don't worry. I've prepared an example that will make it a bit more clear. In this example, we will merge two arrays of eggs. Both of them contain four elements and are already sorted. We start by looking at the first or lowest item of each array, which are 0 and 1. 0 is lower, so we add it to a new array. We repeat the process, looking at the new lowest elements, 1 and 2. 1 is lower, so it is added. And so on. 2 is lower than 3, so it gets added. 3 is lower than 6, so it gets added. 4 is lower than 6. 5 is lower than 6. And now that the rightmost array is empty, we can simply add the two elements that remain in the left array. This produces one large list that contains the elements of both of the original arrays in sorted order. Let's analyze merge sort to determine its efficiency. One component of the algorithm is dividing the array in half in each iteration. And because it's recursive, it will divide it in half again in every iteration. This component has a big O of log base 2 of n, because doubling the size of the original array would only increase the number of iterations by 1, which is a logarithmic function. The other component is merging. Merging is big O of n, because the merging procedure looks at every element in the array exactly once. This combines to make a big O of n log n, which is very exciting, because this is the fastest possible big O for comparison-based sorting algorithms. What's even better, this is a consistent n log n. In the best case and the worst case, and everything in between, it is n log n. This is because the merge sort works the same way no matter what the original array is. I have prepared another example to show how the whole algorithm works. This one's more complicated. It contains 11 elements, and 3 of them are the same. Let's get started. The first part of merge sort is to divide the array in half. I'm choosing to keep the left half one element bigger than the right half in case of an odd array, but you can do it the other way around if you want. Now this is a recursive algorithm, so we need to sort the left side and then the right side. And to begin sorting the left side, you need to divide that array in half. And the left side of that array you have to divide in half as well. Now the left side only has 2 elements, so those two can be merged without any further recursion. In this case, it would just cause the 3 and the 8 to swap. And the rightmost subarray only has a single element, which requires no sorting. Now the array with the 3 and the 8 can be merged into the array with the 6. In this case, the 3 is compared to the 6. 3 is lower, so it gets selected. 6 is compared to 8. 6 is lower, so it gets selected. And 8 is added to the end. Now we sort the right part of the array with the 4, 7, 4. We divide it in half once again. The left part of this has only 2 elements, so they can just be merged which is equivalent to not swapping them at all. The right half only has a single element, so no sorting is required. Now these two halves can be merged, and this presents a bit of an edge case. There are two items with the same value. When comparing these two items, you have to choose the one that's on the left array. And what this does is it keeps the elements in the same order. So if we choose the yellow egg first, the yellow egg will end on the left, which is good because it started on the left. This property is called stability and is useful in some applications. Now the 7 is compared to the green 4, and the green 4 is lower, so that gets added, and then the 7. Now these two lists can be merged together. I'm not going to show the whole merging process again, but it looks like this, and the left half of our big array is sorted. So we can sort the right half in the same array. Divide it in half. The left side contains 3 elements, so divide it in half again. 4 and 5 can be merged directly, which doesn't swap them. 0 is only a single element, so no sorting is necessary. Now the 0 is merged with the 4, 5. And on the right, 1 and 2 can be merged immediately. And these two subarrays are merged. And finally, one more big merge is necessary to merge the left half and the right half and complete the sorting. As you can see, the array is now sorted. And as a bonus, the 3 elements that started as a 4 are in the exact same order that they originally started in. There are a few other properties of merge sort that are important to mention. For one, it is stable. I've already mentioned this, but this just means that if the original array contains multiple elements with the same value, they will remain in the same order as they started once the algorithm is complete. Merge sort can be out of place or in place. The implementation we looked at is out of place, which means it requires extra memory. Specifically, when we merge the two arrays, we create a new array which contains the merged list. This uses extra memory, which is why it's considered out of place. There are other implementations where the merging actually is in place, which means they use less memory. But they are a bit more complicated and can also be slower. Merge sort is a comparison-based sorting algorithm, which means it works by comparing elements together. This means it works on any data type as long as one element of that data type can be compared to another. This contrasts with algorithms like radix sort, for example, which only works on integers. Finally, it's good for both arrays and linked lists. Some sorting algorithms are better for one or the other, but merge sort is fairly good for both. We've been looking at this in the context of arrays, but all the operations I've stated that are required for merge sort can be done pretty easily with linked lists as well. For instance, with merging, it's actually fairly easy to pop an item off a linked list and put it in a new list, probably even easier than it is for arrays. The only tricky part is the original subdividing the array into 2 halves, because you can't easily index into a linked list, but it's still possible to do. Because merge sort is such a simple yet effective algorithm, many variations of it have appeared over the years, and I'm going to show a few important ones. First of all, there are higher order versions of merge sort. In these ones, instead of dividing the array into 2 halves, you divide it into 3 or more equal subdivisions. This has the benefit of requiring less iterations, but each iteration takes a bit longer because the merging procedure is more difficult when there's more than 2 arrays involved. You'd have to compare the lowest element for 3 or more arrays at once. Overall, these can be a little bit slower than merge sort, the regular merge sort in most cases, so they aren't used too much. The natural merge sort is an optimization of merge sort to take advantage of sequences that are already sorted within the array. So for instance, for this array here, regular merge sort would divide it between the 0 and 1, which is halfway in the middle, but natural merge sort would divide it here between the 7 and the 0. This splits the array into 2 parts that are already sorted, and they can be merged immediately without any further recursion required. The final variation I will mention is Tim sort. This is even more optimized than natural merge sort. It's one of the most optimized versions of merge sort at all. It combines merge sort with insertion sort conditionally because there's a few cases, especially for small arrays, where insertion sort would be a little bit faster. So if that case is found within the recursion, it would substitute merging with insertion sort. It has a best case of big O(n), even though the average case is still the same. It's the default sort in Python because of how quick it is. And there's many more variants as well, but these are some of the most important ones. Merge sort's divide and conquer approach to sorting makes it an effective and versatile sorting algorithm. Although other algorithms may surpass it in specific tasks, merge sort's simplicity and efficiency will always make it an excellent choice. Thanks for watching.